Here we have our framework with forces applied, and the first part we'll do will be to draw a freed body diagram, replacing the fixed support with two forces and the roller support with one force. Our free body diagram has been drawn, labeling the forces VA for the roller support at point A and VH and HH for the two forces at point H. After we've drawn our free body diagram, the first thing to prove is that the structure is statically determinate. For that, we'll need to count out our number of members, M, the number of reaction forces, and the number of joints. Number of members: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Number of reaction forces: VA, VH, HH gives us 3 reaction forces. Number of joints: 1, 2, 3, 4, 5, 6, 7, 8. M plus R is 13 plus 3, giving you 16. 2J is 2 times 8. It also gives you 16. 16 equals 16. Therefore, M plus R equals 2J, hence statically determinate. In our structure, we're going to calculate the size of the reaction forces, and for this the same 3 equilibrium equations will apply, namely all the forces in the x direction must add up to give you 0, all the forces in the y direction must add up to give you 0, and taking moments about any point must give you 0 as well. Starting with the first of these equilibrium equations, all the forces in the x direction must add up to give you 0. We only have one horizontal force. It is HH. The arrow is pointing to the left, therefore it is negative. That is the only horizontal force applied. For equilibrium, it must add up to give you 0, or HH equals 0. That's our first reaction force worked out. Now looking at forces in the y direction, we have 3 applied loads, the 4 kilonewtons, the 5 kilonewtons and the 3 kilonewtons, with 2 reactions applied in the opposite direction. So writing down our equilibrium equation for the vertical forces, we have plus VA minus 4 minus 5 minus 3 plus VH equal to 0. Bringing the numbers together, VA plus VH minus 12 equals 0, or VA plus VH equals 12. That'll be 12 kilonewtons. If we know the size of one of the reaction forces, we can then easily work out the other one. Now applying the last equilibrium equation, moments about any point must add up to give you 0. Remember, moments are a force by a distance, and you must state which point you're taking moments about. Usually take it about the first support on the left hand side. That was labelled point A. A with a little bent arrow, shorthand notation for taking moments about point A. And looking at our free body diagram again, VA is the only force applied at point A. Offset distance is 0, so it won't produce a moment. What does produce a moment is the 4 kilonewtons, the 5 kilonewtons, the 3 kilonewtons, and VH. HH doesn't produce a moment. The value is 0 anyway, but the offset distance, HH, acts through point A, so it wouldn't produce a moment if it had a value. It has a value of 0, so it doesn't produce a moment anyway. Writing down our moment equations, 4 kilonewtons for the force. Distance from A to the 4 kilonewtons is going to be 3 meters. The next force is 5 kilonewtons, and it's 6 meters across from point A to that force. Next one is 3 kilonewtons. It's 9 meters across from point A. And the last one is VH, and it's 12 meters across. All these moments for equilibrium must add up to give you 0. We're now going to consider clockwise moments, anti-clockwise moments, to put a sign in front of each of these brackets. Clockwise moments are positive, anti-clockwise moments are negative. Looking at our free body diagram, for each of the forces in turn, consider them on a piece of string, allowed to freely rotate. You're holding the end of the string at point A. How would the 4 kilonewton force want to rotate around point A? And it would want to return round in a clockwise, positive manner. Do the same for the 5 kilonewtons. Again, holding your piece of string. How would the 5 kilonewtons want to rotate around point A? It would want to rotate around in a clockwise manner, clockwise moment. 3 kilonewtons, holding the piece of string, again at point A. The 3 kilonewtons would want to turn round in a clockwise manner, clockwise moment. The VH, again holding that piece of string at point A, the arrow on VH would want to turn around in an anti-clockwise direction, therefore a negative moment. Updating these values into our equation, plus, 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 minus, then rearranging our equation, 12 plus 30 plus 27 minus 12, VH equals 0. Adding the numbers together gives us 69. Take the 12 VH to the other side of the equal sign, it becomes positive. Then divide through by 12, gives us the value for VH, and that would be 5.75 kilonewtons. That's our first, that's our second actually reaction force worked out. Then using the other equilibrium equation we had worked out earlier, VA plus VH is equal to 12 kilonewtons. Substituting in our value, that's 12, then rearranging our equation, 12 minus 5.75 gives us VA to be a value of 6.25 kilonewtons. For the next part, which is to calculate the forces in the members, in this problem we're only going to work out the force in 6 members. Member AB, AC, CD, CE, BE and BD. For this we will do the resolution of joints method, resolving the forces at each of the joints. before we start to resolve the forces at our first joint, onto each of the members we're going to draw a set of arrows. Arrows are going to be pointing towards each other, representing tension. This will go on to each member and will help us to resolve the forces at each joint. To work out the force in our first members, we're going to start at joint A and isolate the forces we have at joint A and apply our equilibrium equations. Drawing out a free body diagram of joint A gives us our applied reaction force, and following the arrow notation we have, horizontally we have force in member AC, or force AC, and at an angle of 30 degrees we have force AB. Now we're going to resolve this little small free body diagram in the vertical direction. FAB times the sine of the angle, 30 degrees, plus VA. For equilibrium, must add up to give you 0. Force AB sine 30 plus 6.25 for VA should give you 0. Rearrange our equation. Negative 6.25 on the other side, then finally divide through by the sine of 30 degrees, gives us the force in our first member, and force AB is minus 12.5 kilonewtons. The minus sign indicates that the force is actually a compressive force instead of a tension force. Now resolving the forces in the horizontal direction for the same joint. Force AC plus force AB, this time times the cos of your angle. For equilibrium, must add up to give you 0. Force AC, substituting in your value, minus 12.5. Multiplying it out gives you 10.83. Finally, moving the negative number to the equal sign gives you 10.83 kilonewtons. That's the value for the force in our next member. It's positive, indicating that it's a tension force. Next, we're going to look at joint C and isolate the forces that are at joint C. And here we can see this is our system of forces we have at joint C. So drawn a small freed body diagram. Following the same arrow convention that we have. force BC going upwards, 4 kilonewtons acting down, force AC acting to the left, and force CE acting to the right. Applying our equilibrium equations, doing the vertical, so we have plus force BC going upwards, minus 4 going downwards. Rearranging the equation, force BC is a positive 4 kilonewtons. Now doing the horizontal resolve, force CE, positive to the right, minus force AC, negative going to the left. They must add up to give you 0 for equilibrium. Force CE equals force AC. Force AC we have previously worked out, and it was a positive 10.83 kilonewtons. Then finally, to do our last joint, joint B, we're going to isolate the forces at joint B. And before we draw our free body diagram, I'm going to draw on some angles. Through simple triangles, the angle at B here is going to be 60 degrees. Again, on triangle BCE, right angle degrees, angle here is going to be 60 degrees, and straight line, so the final angle here is also going to be 60 degrees. Drawing our free body diagram of joint B, gives us force BD, force BE, force BC, and force AB. The angles between each of the lines here being 60 degrees. To do the analysis on this joint, there's two ways we can do it. We can do our vertical and horizontal resolve on the joint as it stands. If we do that, we'll have two equations, two unknowns. However, the equations that do drop out, you'll have to solve using a pair of simultaneous equations. However, because equilibrium applies everywhere, what we can do is to take this joint and effectively turn it around so that the member AB and B to D is now horizontal, and we can do our equilibrium equation based on it horizontally. So redrawing our member by turning it around 30 degrees clockwise. Force AB, force BD, and our two forces, force BC, force BE. Again, the angles between each of these members is 60 degrees. All I've just done is turn it around 60 degrees. The reason for doing this is whenever we do our equilibrium equations, we'll have one equation with one unknown, and then we can directly solve it. Previously, if we didn't rotate around the joint, it would then you'd have to solve the unknown forces in the members by using simultaneous equations. Now with the joint rotated, we can now do a vertical resolve, and that would give us minus force BC using the angle of 60 degrees to the horizontal, minus force BC sine 60 degrees minus force BE sine using this 60 degrees. For equilibrium, they must add up to give you 0. 60 degrees will cancel from both sides. Minus force BC minus force BE equals 0. Force BE we already know, which was a value of 4. Taking force BE to the other side makes it positive, so we have our first value here. Force BE is equal to negative 4 kilonewtons, the minus sign indicating a compression force. Now doing the horizontal resolve on the same joint, minus force AB plus force BD minus force BC now times the cos of 60 degrees plus force BE cos 60 degrees. For equilibrium, they must all add up to give you 0. Force AB was minus 12.5, careful about the double negative. Force BD is the one we're trying to calculate. Force BC, as earlier, is a value of 4. Force BE is a value of negative 4. Working this through, 12.5 plus force BD minus 2 and another minus 2 equals 0. Force BD plus 8.5 equals 0. Force BD is minus 8.5 kilonewtons. In this framework, we were only asked to calculate the forces in the following members: member AB, member AC, member BC, member CE, member BE, and member BD. For that, we needed to analyse the forces at 3 joints: joint A, then joint C, then joint B, and the results we got was force AB was minus 12.5 kilonewtons, force AC was 10.83 kilonewtons, force CE 10.83 kilonewtons, force BC 4 kilonewtons. Force BE was minus 4 kilonewtons, and finally force BD was minus 8.5 kilonewtons. Remembering, positive values are for tension forces and negative values are for compression forces.